right, we are doing 18.2 now. So 18.2 are special right triangles. All right, so far what we've been dealing with are right triangles that, I need a pen. Okay, so we have these, that's a beautiful right triangle. Just kidding, it's terrible. So what we've been dealing with are right triangles, right? And we know like 3, 4, and 5. We know that the sum of the square of the sides are equal to the hypotenuse squared. All right, so with that, we know 5 squared is equal to 3 squared plus 4 squared. 3, 4, 5 is one type of special right triangle. It's a Pythagorean triple triangle, and they are Pythagorean triples named after Pythagoras, who absolutely loved them because they were whole numbers. So 3, 4, and 5 are whole numbers. Otherwise, they have radicals involved which are irrational, and they never end, and they become quite a bother. Well, we're going to talk about some other right triangles that are special, and they do have radicals, unfortunately. But anyway, they're not Pythagorean triples, but they're different than those, and they're all right because they're really useful, and especially when we get into trigonometry and we're dealing with the unit circle and different angles and triangles, reference triangles with the unit circle. They're all about these special right triangles. So recall or remember, if you have an isosceles triangle has two sides that are equal and two base angles that are equal, if you recall. So if it's a right triangle and it's an isosceles triangle, right, that means this side and this side are the same, and this angle is the same, right? So isosceles triangles have two sides congruent, and those are called legs that are congruent, and two angles that are congruent that are called base angles, if you recall that. So the measure of angle A and measure of angle C have to be equal because it's an isosceles triangle. Now, that also means the two side lengths are equal. But if we have a 90-degree angle right here, the other two angles have to share 90 equally, and therefore, what would they be? They would each have to be 45 degrees, right? And they're the same. So this would have to be a 45-degree angle, and this would have to be a 45-degree angle if it's an isosceles right triangle, because they're equal and they share 90. So 90 divided by 2 is 45. Now, an isosceles right triangle is also called a 45, 45, 90 special right triangle. 45, 45, 90. So we know all the angles for sure. Now, the side measures are, of course, depending on how big or how small the triangles are, all going to be different. But let's look and see what happens, because a really special thing happens, which is why we call them special right triangles. So if you're using Pythagorean theorem to solve for x, we have two legs that are 1 and 1. So x is going to equal the square root of 1 squared plus 1 squared, right? Sum of the legs squared. And under the radical, and that's 1 squared is 1. So we have radical 2. So x is radical 2. Now for this unit specifically, we're going to leave everything in radical form, in exact form, which is fine and great, and we do that all the time in higher level math courses, of course, because radical 2 is nice. It's perfect. It's exact. It's just radical 2. We don't have to worry about a never-ending decimal with that. All right? Now, if we're solving for example 2, notice that we have x for our leg, and because both legs are equal, that other leg would also be x. And to set up Pythagorean theorem, this is going to be we're not going to be able to use our little shortcuts already solved because we have two sides that have x's. So we know x squared plus x squared is equal to 1 squared. Leg squared plus leg squared equals the hypotenuse squared. So x squared plus x squared is 2x squared, and that's equal to 1. And then divide by 2, where we have x squared is 1/2, and then square root, and we get 1 over radical 2. Now I'm going to leave it like that. I know it's not rationalized, but we know 1 over radical 2 are those two sides. All right, now I'm going to erase this little x here because we found it to be 1 over radical 2. Now, it's going to be kind of crazy, but look at this and see if you can see anything kind of cool. All right, when the sides, look at these two examples. So when the sides are 1, 1, we multiply 1, by radical 2, and we get the hypotenuse radical 2. I should probably use times a little dot so we don't get confused with the x. So if we times radical 2, we get the hypotenuse. If the hypotenuse, whatever it is, 1, to get the leg, we divide by radical 2, don't we? Now is that odd or what? So that's why it's a special right triangle. An isosceles right triangle is a special right triangle. It's because, well, let's do a few more and then we're going to see. But just wanted to point out, sides are 1, multiplied by radical 2 to get the hypotenuse. If the hypotenuse is 1, we divide by radical 2 to get back to the side. Now let's check this out. Okay, example 3. If this is 45, this is 45. And that means the sides opposite them are congruent. So if that side's 8, this side's also 8. Okay, so that gives us 2 of the 3 sides that we can use the Pythagorean theorem to solve. So we know that y is going to equal the square root of the legs squared and summed. 8 squared plus 8 squared. So that's going to be 64 plus 64, which is radical 128. And if we put that in our calculator, okay, so radical 128, we get 8 radical 2. Ooh, that's kind of odd, isn't it? Every time I do that, I lose my pen. 8 radical 2. I have 2 sides that are 8 on a 45, 45, 90 special right isosceles triangle, and the hypotenuse is 8 radical 2. Well, that's kind of similar to if the 2 sides are 1, the hypotenuse is 1 radical 2. Now if the 2 sides are 8, the hypotenuse is 8 radical 2. And in fact, there's a theorem that states if you have a special isosceles right triangle, and so you have a 45, 45, 90 triangle, whatever the legs are, they'll be the same because they're the base, the sides that are congruent. The hypotenuse will be whatever that side length is times radical 2 every time. All right, now we have this other one up here, 1 divided by radical 2. Now, if I have this next triangle, these two are the sides that are the same, right? So I'm going to just use x and x to solve for them. So x squared plus x squared is 19 squared, all right? So 2x squared is 19 squared. Divide by 2. So I have x squared is 19 squared divided by 2. Now notice I'm just leaving 19 squared. I just want to do that because eventually I'm going to square root, right? So when I square root, 19 squared square rooted is just 19 over radical 2. So once again, I have the side is going to be whatever the hypotenuse is divided by radical 2. If it's 1, we divided by radical 2 to get the side. If it's 19, we still divided by radical 2 to get the side measure. And that is true for all isosceles right triangles. So if you look at the given a leg, okay, I know the other 2 sides. This is going to be a, and this is going to be a radical 2. Because I know the leg, I'm going to multiply by radical 2 to get to the hypotenuse in a 45, 45, 90 triangle. If this is b, these 2 sides will be b divided by radical 2 because it's a hypotenuse I know. All right, so get to from hypotenuse to leg, we divide by radical 2. To get from leg to hypotenuse, the opposite way around, we multiply by radical 2, whatever the side is, or whatever the hypotenuse is. Okay, that's pretty interesting, isn't it? So that's going to be the case. I wanted to see, did we have any other examples for 45, 45, 90s to do? I'll just go right into a 30, 60, 90. Okay, so that's fine. We'll deal with that in a minute. So equilateral triangles are something different. Equilateral triangles mean all 3 sides are the same, right? If it's equilateral, it's also equiangular. So all 3 of these angles Okay, these two, and the third one will all be 60 degrees, right? But this one, AD becomes a perpendicular bisector. Remember, bisector divides the angle into two equal parts, giving each of these angles a 30-degree measure. Okay, that's what happens every time. So the measure of angle C is going to be 60 degrees. We'll just write it underneath that. The measure of angle CAD, which C to A to D is this one right here, was a 30-degree angle. So all of a sudden now we have a 30, 60, 90 special right triangle. And triangle that is equilateral, that has a perpendicular bisector split right down the center, makes two congruent triangles that are 30, 60, 90 triangles. All right, now if AC is 4, all right, then what will DC be? If AC is 4, DC is going to be half of 4 because this whole side will be 4. So DC will have to be 2. And if DC is 12, so if DC right here is 12, then AC would have to be double that, which would be 24. Okay. So always you're going to notice that whatever this side is of this triangle, a 30, 60, 90 triangle, if it's, I should erase all these markings. You'll notice that, erase please. All right, you'll notice that in this triangle, I have to be careful with time. If DC is 2, the hypotenuse is 4, right? And then if DC is 12, AC is 24, the hypotenuse of this 30, 60, 90 triangle is always twice that other leg. And that makes a 30, 60, 90 triangle. All right? If we're using Pythagorean theorem to solve for x and we have a side that's 1, we know this has to be 2 because it's an equilateral triangle. And to come up with x, we would do square root of 2 squared minus 1 squared, which is square root of 4 minus 1, which is square root of 3. And we're just going to leave it square root of 3. Okay? And then example 2, if I know this is 1, DC would be 1/2. And then I would have the square root of 1 squared minus 1/2 squared, because we have the hypotenuse in the leg, and we subtract the square of the sides. That's 1 minus 1/4, which is square root of, we have 4 over 4 to get a common denominator, 3/4, which is square root of 3 over square root of 4, which is 2. Right? So those are all the sides of the triangle. And I would like to, I guess we're going to use Pythagorean theorem to do 3 more problems before we finish this up. So I'm going to stop it because we're close to the 15-minute mark that I need to stop so it'll upload easier as a video. And so just stop now and we'll move on to part 2 and you'll get the rest of it.